I want to kick things off today with a very special, highly specific shout out, actually.
Oh,
Yeah,
yeah.
yeah, we are dedicating this deep dive to a really motivated group of listeners who wrote in.
Okay.
They are the Bussen Sigma Scholars of Edward Little High.
That is quite the title. I love it.
Right. And now, I know what some of you are thinking. You hear a term like Sigma, and you immediately think of, internet culture.
Right, the whole lone wolf thing.
Exactly. The lone wolf mentality. The person who is operating outside the standard hierarchy.
Yeah.
Someone who doesn't just, blindly follow the rules, but bends them or completely rewrites them to achieve their own goals.
Right.
And while it might be popular slang right now, I honestly couldn't think of a more perfect framing for what we are exploring today.
It really is perfect.
Because scientifically speaking, a sigma is the ultimate outlier.
Mm-hmm.
And today, we are looking at how the universe itself, or, well, at least the most advanced systems we can engineer within it, employs that exact same sigma independence.
Yeah, that's exactly what it is.
We're looking at how systems deliberately break the most basic foundational rules of physics to achieve absolutely incredible, otherwise impossible things.
It's actually a brilliant lens to view this through, because the most basic rule of physics, the one that makes the universe predictable and safe, is linearity.
Yeah.
It's the principle of superposition.
Right.
If I have a linear system and I put in two separate signals, they just travel right through, independently.
Like they don't interact at all.
Exactly, and they just add up at the end.
Yeah.
1 + 1 = 2. It's clean, it's proportional, and frankly, it is incredibly boring.
It's too simple.
Right. If you want a system to actually do something interesting, if you want it to actively create or select or process information,
Yeah.
or to route energy or fundamentally reshape its own structure, linearity is a dead end. You have to break the rule of superposition.
You have to break the rule.
You have to introduce what we call nonlinear connectors.
And that is our mission for this deep dive. We are going to explore the profound science of coupling, how we connect different components in complex systems
Yeah.
using these nonlinear cheat codes.
Yeah, they really are cheat codes.
We have a fascinating stack of research in front of us, and we are going to trace this mechanism across wildly different domains today.
We're covering a lot of ground.
We really are. We are starting in the digital brains of deep neural networks. Then we'll look at the chaotic physics of classical mechanical resonators. So think massive bridges and skyscrapers.
All right.
After that, we'll shrink down to the cutting-edge physics of modern cavity optomechanics, where light literally pushes matter around.
Which is wild.
It is. And finally, we'll land in the ultra-cold, perfectly clean world of superconducting quantum circuits.
What stands out to me here is that despite these physical substrates being completely different, lines of code, massive steel springs, microscopic mirrors, quantum states.
Yeah, they have nothing in common physically.
Right. But the underlying mathematical paradigm is identical.
Wow.
In a linear regime, signals propagate independently. They preserve their topology, their dimensionality, but a nonlinear connector acts as a structural transformation. It makes the system's response dependent on its own state. It is the core mechanism for structural composition across both the digital and physical worlds.
Okay, let's unpack this. Starting with the digital world. Because to understand how nonlinear coupling shapes the physical universe, we first have to see how it radically reshapes the digital world of data.
Absolutely.
Let's talk about artificial intelligence, specifically deep neural networks.
So to set the stage, the fundamental goal of a deep neural network in machine learning is to take complex, messy data, say the raw pixels of an image,
Sure.
and transform that data distribution into a representation where it can be easily separated and classified.
Like, is this an image of a dog or a cat?
Exactly. To do that, the network has to draw a boundary.
Okay.
But here's the massive problem with linear AI. Without a nonlinear activation function, a feed-forward neural network mathematically collapses into a single linear transformation.
Wait, it just collapses.
It does. I don't care if it has 2 layers or 2,000 layers. If it's all linear, it just boils down to a single series of matrix multiplications.
I always picture this like trying to separate a pile of red and blue marbles that are completely mixed together on a flat table.
That's a good way to look at it.
But in a linear system, you are only allowed to use a straight, rigid ruler to draw a single line between them.
Right.
If you have a simple cluster of red on the left and blue on the right, fine. But what if the red marbles form a circle in the middle and the blue marbles are surrounding them? The classic concentric circles problem.
Oh yeah, a straight ruler is completely useless there.
You literally cannot draw a single straight line to separate them.
You've hit on the exact limitation. In high-dimensional data spaces, those straight lines are called flat hyperplanar decision boundaries.
Flat hyperplanar boundary.
Yeah. And they fail spectacularly at real-world complexity. Consider the XOR problem.
Right, the exclusive or logic puzzle. Like saying, I want a sandwich with either peanut butter or jelly, but if you give me both, it's ruined.
Perfectly stated. On a graph, the XOR problem places your acceptable options diagonally across from each other,
Okay.
with the unacceptable options on the opposite diagonal.
Right, they're crossed.
So try laying a single straight ruler across a graph to separate those diagonals.
It's impossible.
It's totally impossible. So the solution is the activation function. The activation function acts as the non-linear connector between the layers of the network.
Right.
It takes the linear output of a neuron and warps it. It bends, folds, and reshapes the input space itself, allowing the network to construct high-dimensional spaces with highly curved decision boundaries.
So instead of just sliding a straight ruler around on a flat table, these nonlinear connectors are essentially letting the neural network pick up the table itself
Yes.
and fold it, crease it, and warp it so that all the red marbles end up on one side of a three-dimensional fold and all the blue marbles end up on the other.
That is the perfect visualization. And our sources detail a few specific types of these nonlinear connectors, each with its own geometric signature.
Okay, let's hear them.
First, you have polynomial neurons.
Okay.
Instead of just passing a signal through, they incorporate polynomial terms, so squaring or cubing the input data.
Right.
By doing this, they allow the network to model higher-order interactions between input features.
So what does that actually look like for the marbles?
The result is that the network can draw these beautifully smooth, global, highly curved decision boundaries.
Okay, so folding the table works if the marbles are generally split in some broad, swooping pattern.
Right.
But what if my red marbles are clumped together in little isolated islands all over the table? A single smooth fold across the whole table won't help me isolate those tiny pockets.
And that requires a completely different type of connector. For that, we use something called a radial basis function, or RBF.
RBF, yeah.
Instead of a global fold, an RBF takes a localized approach. It measures the distance from a specific center point and creates a localized activation region.
So it's very targeted.
Exactly. It creates a boundary that wraps precisely around those tight local geometries, those isolated islands you mentioned, without warping or affecting the rest of the space.
That makes sense. But the absolute workhorse of modern AI, the one you hear about constantly, is the ReLU, the rectified linear unit.
Yes, the classic ReLU.
However, our sources focus on a very specific variant called leaky ReLU. Why do we need it to be leaky? What is leaking?
To understand the leak, we have to understand the flaw in the original.
Okay.
The standard ReLU is mathematically very simple. If the input is a positive number, pass it through exactly as it is.
Easy enough.
If the input is negative, output exactly 0.
Okay.
Geometrically, it creates piecewise linear boundaries with a sharp localized crease, literally a hard crease in your folded table analogy.
Right, a sharp fold.
But there's a fatal flaw called the dying neuron problem.
Meaning the neuron just stops working.
Essentially, yes. During training, the network is constantly updating the weights of its neurons based on errors. But if a neuron's weights get pushed into a state where it only ever receives negative inputs from the data, its output is always 0.
Because anything negative becomes a 0.
Exactly. Because the output is 0, the gradient, which is the mathematical slope used to update the network, also becomes 0.
So it gets no feedback.
None. It receives no feedback. It stops learning completely. It is dead.
Wow.
Leaky ReLU fixes this by allowing a tiny non-zero gradient in the negative regime. Instead of a flat 0, it gives a very slight slope.
So it leaks just a tiny bit of information through.
Exactly.
That ensures that even if the neuron is pushed deep into the negative, it isn't totally deaf.
Right.
It can still hear the feedback, update its weights, and eventually pull itself back out.
Precisely. It maintains a continuous folding process, ensuring much more robust training across the entire network.
I get the math, and the folding table analogy really helps, but I have to push back a little here.
Sure.
Doesn't adding all these curves and polynomials and folds make the network incredibly chaotic?
It does.
If we're talking about high-dimensional spaces being folded over and over again, millions of times across thousands of layers, doesn't that dimensionality complexity trade-off make the whole system too computationally expensive and totally opaque.
That is the defining tension in modern deep learning. The dimensionality-complexity trade-off is the razor's edge we walk.
Yeah.
You want the network to be highly expressive, but if you let it fold the space too chaotically, it just memorizes the training data.
Right. It overfits.
It overfits. And you are right about it becoming opaque. That brings us to one of the most fascinating concepts in the research, which is space folding, and how we actually probe it.
Okay, let's get into that.
When a network uses ReLU activations, it takes the continuous Euclidean input space, so the normal smooth geometry we live in, and folds it into a discrete Hamming activation space.
A Hamming space, let's define that. That basically means the network isn't looking at smooth gradients anymore, it's just looking at patterns of ones and zeros.
Well,
right.
That's it.
A neuron is either firing or it isn't.
Yes. For any given input image, you get a unique binary signature of which neurons are active across the entire network.
Yeah.
But because it is a black box, it's very hard to tell if the network has actually learned the deep semantic structure of a dog, or if it's just reacting superficially to the specific lighting or background of the one picture you showed it.
Right, like maybe it just thinks a green background means dog.
Exactly. To figure this out, researchers use a technique called APEX. That's activation perturbation for exploration.
So how does APEX actually work? How does it map that chaos?
Traditionally, to test a network's robustness, you might add noise to the input image, like static on a TV, and see if it still recognizes the dog.
Sure, just fuzz up the picture.
Right. APEX does something completely different. It keeps the input image perfectly clear, and it keeps the model's weights locked.
So?
Instead, it injects Gaussian noise directly into the hidden layers right after those nonlinear activation functions fire. It perturbs the space folding itself.
Wait, so you aren't shaking the camera. You are shaking the folded table while the marbles are rolling down it.
That is a phenomenal way to put it. And APEX reveals a brilliant transition in the network's behavior.
What happens?
When you inject a small amount of noise, you are probing the local regularity. You are testing if that specific crease in the table is robust.
Okay.
But as you turn up the noise into the large noise regime, you force the network to abandon the specific input image.
Because it's shaking too much.
Right. The signal of the dog is drowned out by the shaking of the table. But the network still has to output a prediction. And this is where it gets slightly eerie.
Eerie how?
The network transitions from a sample-dependent reaction to displaying its own deeply ingrained model-dependent behaviors and biases.
It defaults to whatever shape it's most comfortable in. It defaults to its deepest folds.
Exactly. The underlying topology of the manifold takes over, completely independent of the input. APEX exposes the global training-induced biases of the model. In fact, if a model has been maliciously compromised, say if a hacker slipped a backdoor into the training data to make the AI always classify a stop sign as a speed limit sign.
Oh, that's scary.
Right. Well, APEX will reveal it. Under high internal noise, a backdoored model will show a massive concentration of predictions towards that specific backdoor target.
Because it's such a deep fold.
Yes. Because during training, that target was aggressively carved into the manifold as a massive gravitational well. The marbles can't help but roll into it when you shake the table.
So what does this all mean? It means that in the digital realm, nonlinear coupling isn't just a math trick to get better scores. It is a structural necessity.
It really is.
It's the mechanism that takes flat, useless data and literally warps the geometry of the information space until the answers fall out.
Yeah.
But here is where I want to pivot. Because that is data. That's math running on silicon. The digital realm is abstract. So if neural networks use nonlinear coupling to fold data space, how do physical machines use nonlinear coupling to fold actual physical space and route real kinetic energy?
To bridge that gap, we have to look at the physical equivalent of space folding. In classical mechanics, this is known as phase-space bifurcations.
Okay.
And we see this most clearly in classical multi-degree of freedom resonators.
That's a mouthful.
It is. But I want you to picture a massive physical system. A suspension bridge holding hundreds of cars, or the wing of a commercial airliner, or even the microscopic moving parts in a MEMS device inside your phone.
Okay, I'm picturing it.
These are primary oscillators. They vibrate.
Naturally.
Right. And if they are subjected to a harmonic excitation, say wind hitting the bridge at a constant rhythm or an engine vibrating at a specific frequency, that linear vibration can build up, resonate, and eventually tear the structure apart.
Everyone has seen that classic, terrifying physics class video of the Tacoma Narrows Bridge twisting in the wind until it just completely disintegrates.
Exactly. That's resonance destroying a structure. The traditional engineering solution to prevent that is to add a linear damper, like a massive shock absorber, which just broadly dissipates energy as heat.
Sure.
But the sources outline a far more sophisticated nonlinear approach, coupling the primary oscillator to an ungrounded 2-degree of freedom nonlinear energy sink, or NES.
A nonlinear energy sink. It sounds intensely futuristic. What is it, practically speaking?
Practically, it's brilliant engineering. You attach a secondary mass to the primary structure, but you don't connect it with a normal linear spring.
Okay.
In a normal spring, the force is proportional to the stretch. Pull it an inch, it pulls back with 1 pound of force. Pull it 2 inches, it pulls back with 2 pounds.
Right, totally linear.
Instead, you connect this NES via a nonlinear coupling, specifically modeled on a Duffing oscillator, which uses cubic stiffness.
Okay, let's break down cubic stiffness. How does that feel different from a normal spring?
In a cubic spring, the restoring force scales with the cube of the displacement. If you pull it 1 inch, it pulls back with 1 unit of force. But if you pull it 2 inches, it doesn't pull back with 2 units, it pulls back with 8 units.
Oh, wow.
If you pull it 3 inches, it pulls back with 27 units. It gets exponentially stiffer the further you push it.
So how does an exponentially stiff spring save a suspension bridge?
Because of that cubic nonlinearity, the NES does not have a fixed resonant frequency. A linear spring only vibrates at one specific pitch, no matter how hard you hit it.
Okay.
But the NES can effectively tune itself. It can resonate at a wide range of frequencies, depending entirely on how much energy is being pumped into it at that exact moment.
Wait, really?
Yes.
Yeah.
This isn't just about passively bleeding off energy. It's about targeted, dynamic energy routing.
So it's actively seeking out the dangerous vibrations.
In a mechanical sense, yes. When the primary system, the bridge, starts to vibrate dangerously close to its breaking point, the NES engages.
It wakes up.
Exactly. It initiates a phase-space bifurcation. Mathematically, it suddenly opens up a completely new dynamic pathway that didn't exist a moment before.
Wow.
The NES acts as a sponge for chaos. It literally sucks the kinetic energy out of the primary system right near the point of resonance, effectively suppressing the chaotic divergence.
It just pulls it away.
Yeah, it undergoes what we call nonlinear energy pumping, violently oscillating itself, absorbing all that destructive force while leaving the primary structure completely calm and stable.
That is incredible. The nonlinear spring takes all the chaotic, destructive kinetic energy that was going to tear the bridge apart, and it folds the physical dynamics of the system so that the energy is neatly routed into this harmless little secondary mass.
That's exactly it.
But wait, this brings up a huge question. If this cubic spring is so wild and variable, how do engineers even design it? How do you calculate the safety of a bridge if the shock absorber behaves totally differently depending on the wind speed?
You are touching on the exact mechanism of control here. It requires a mathematical technique called equivalent linearization.
Equivalent linearization.
Yes. Just as the neural network maps continuous space to discrete space to make it manageable, physicists translate the wild, nonlinear cubic stiffness of the NES into something they can calculate.
Oh, I see.
They figure out an equivalent linear representation that captures the dominant dynamics, an amplitude-dependent frequency and an amplitude-dependent damping rate.
So they basically translate the nonlinear chaos back into a linear language just long enough to run the safety math.
Exactly. This makes the wild physical vibrations mathematically tractable. You tame the chaos by wrestling the nonlinear behavior into a framework you can calculate, allowing you to build structures that are incredibly resilient.
Okay, so we've seen massive physical energy routed by springs and masses using cubic stiffness as the nonlinear connector.
Yeah.
We're talking about macroscopic forces, wind, steel, concrete, but I want to pivot again. What happens when we take this exact same concept and shrink it down? What happens when the mass we are trying to couple with is just a single particle of light?
Now we are entering the realm of cavity optomechanics, which is honestly one of the most mind-bending fields of modern physics.
I am ready.
We are scaling the conversation down from bridges to the micro and nanoscale. Optomechanics is the study of coupling light, which are photons, with mechanical motion, which are phonons.
Okay.
And we do this inside optical cavities.
Okay, let's paint a picture for the listener.
Imagine two microscopic mirrors facing each other. One mirror is fixed, heavy, and immovable.
Right.
The other mirror is suspended on a tiny microscopic cantilever. It's flexible, it can swing back and forth.
Yep.
We trap a laser beam between them. What is physically happening in that space?
There are two distinct physical forces at play here, acting as our couplers between the light and the matter.
Okay.
The first is radiation pressure. When a photon bounces off a mirror, it has momentum. It's a tiny, almost imperceptible amount of momentum.
But because this optical cavity has what we call high finesse, meaning the mirrors are incredibly reflective, that single photon doesn't just bounce once.
It keeps going.
It bounces back and forth thousands of times before it eventually escapes. And every single time it hits that flexible mirror, it transfers a tiny kick of momentum. The cavity acts as a multiplier, turning the whisper of a photon into a tangible mechanical force.
I always picture this like throwing ping pong balls at a sheet of paper.
Okay.
One ping pong ball hitting the paper does basically nothing.
Hmm.
But if you have a machine gun firing 1,000,000 ping pong balls a second, the sheer momentum will push the paper backward.
That captures the mechanical push perfectly.
Nice.
But there is a second force at play, the photothermal or bolometric force.
Photothermal, so heat.
Right. As the photons bounce around, they aren't all perfectly reflected. Some of them are absorbed by the material of the mirror itself. This absorption heats the material, creating a tiny temperature gradient.
Oh, interesting.
And because materials expand when they heat up, this thermal expansion actually causes the microscopic mirror to physically bend or deflect.
Okay, so the light is pushing the mirror with momentum and bending the mirror with heat. That is the coupling. But where does the nonlinearity come in? So far, that just sounds like action and reaction.
The nonlinearity arises from the feedback loop between the light and the mirror, which we call dynamical backaction.
Dynamical backaction.
This is the ultimate feedback loop. As the mirror moves, whether pushed by momentum or bent by heat, the physical length of the cavity changes.
Right.
If the cavity gets longer or shorter, its optical resonance frequency shifts.
Right, because the cavity is tuned to only let light in if the wavelength exactly fits the distance between the mirrors, almost like a resonant musical note in a flute.
Exactly right. So as the mirror moves, the cavity's tuning changes. This changes how much laser light can actually enter the cavity from the outside, which in turn changes the number of photons bouncing around inside, which then changes the radiation pressure pushing on the mirror. The force depends on the position, and the position depends on the force.
That's a crazy loop.
It is. If we connect this to the bigger picture, this isn't an instantaneous reaction. Light is incredibly fast, but the photons spend a finite amount of time bouncing around inside the cavity. They have a finite lifetime.
Okay.
This creates a phase delay between the mirror's motion and the radiation pressure force. And in physics, a delayed force translates into two specific things. It manifests as an extra spring stiffness or an extra damping effect.
Wait, so...
The light literally acts as a programmable spring and a programmable shock absorber for the physical mirror.
So we are literally using light to dictate the physical mechanical properties of matter.
We are.
And this leads to what the sources call the detuning cheat codes. Because you can tune the laser you're shining into the cavity to be slightly off resonance. You can tune it slightly lower in frequency, which they call red detuned, or slightly higher in frequency, blue detuned.
Right.
Let's walk through what happens in each scenario, because the outcomes are wildly different.
Let's start with a red detuned pump. In this scenario, you are driving the system on the lower sideband, known as an anti-Stokes process.
Okay.
The photons entering the cavity are slightly too cold or too low in energy to resonate perfectly between the mirrors.
They need a boost.
Exactly. So to fit inside the cavity, they steal energy from the mechanical oscillator. They absorb a phonon, a quantum of mechanical vibration, to boost their own energy and match the cavity resonance before escaping.
Wow.
Every time a photon does this, it removes heat and kinetic energy from the mirror. This process can literally cool the macroscopic mechanical object all the way down to its absolute quantum ground state.
You're freezing solid matter using light. Okay, freezing matter with light is wild enough, but what if we go the other way? What happens with blue detuning?
With the blue detuned pump, the Stokes process, the photons entering the cavity have slightly too much energy. To resonate, they have to shed energy.
So they dump it into the mirror.
Exactly. They deposit phonons into the mechanical oscillator. They amplify the mechanical motion. This creates exponential growth in the vibration.
That sounds dangerous.
It is, but crucially, in the quantum realm, this specific interaction generates two-mode squeezing and quantum entanglement between the light field and the mechanical motion.
Wait, I have to point out a paradox here from the sources.
Oh, sure.
We talked about radiation pressure and the photothermal force. The sources explicitly note that photothermal forces can actually reverse this normal radiation pressure rule.
Yeah.
Depending on the thermal expansion properties of the specific material you use for the mirror, a red detuned laser might amplify the motion, and a blue detuned laser might cool it. It is like the universe left a loophole in the laws of thermodynamics just to mess with us.
It is a remarkable loophole, and it demonstrates how carefully these nonlinear couplings must be engineered. But the complexity doesn't stop with just two modes.
There's more.
Oh, yeah. The sources introduce a burgeoning field called magnomechanics. Here, researchers introduce a YIG sphere, yttrium iron garnet, into a microwave cavity.
Okay.
YIG is a highly magnetic material, and it introduces a third element to couple with, which are magnons.
Let's pause and define that. We have photons, which are light. We have phonons, which are physical vibration. What is a magnon?
A magnon is a quantum of magnetic excitation. Think of it as a spin wave rippling through the magnetic material.
Okay.
So now scientists are coupling the mechanical phonon mode to two independent bosonic normal modes simultaneously.
The bosonic normal modes is just physics jargon for independent types of waves that can coexist without interfering with each other, right?
That's a great way to simplify it. And by coupling the physical vibration to both the light wave and the magnetic wave simultaneously, scientists achieve something called dynamical back-action evasion.
Evasion, like dodging a bullet.
In a sense, yes. In quantum mechanics, the act of measuring a system typically ruins its state. That's the core of Heisenberg's uncertainty principle.
Right.
The measurement itself introduces quantum back-action noise.
Because you have to interact with it to measure it.
Exactly. But by carefully balancing this three-way nonlinear coupling, the back action from the light wave perfectly cancels out the back action from the magnetic wave.
Oh, wow.
It allows scientists to measure the mechanical system with extreme precision without the measurement itself destroying the delicate quantum state.
Okay, that makes sense. But wait, I have a massive question about the blue detuning we just talked about.
Yeah.
If blue detuning makes the system unstable by constantly depositing energy and creating exponential growth in the vibrations, how can we possibly use it to create and control a delicate quantum entangled state? Wouldn't the whole thing just violently blow up and vibrate itself to pieces before you could use the entanglement?
That is the exact problem that requires time-continuous quantum control. You cannot just turn on a blue detuned laser and walk away. The system is inherently unstable. To harness that entanglement without destroying the system, you have to constantly monitor the output light using a technique called homodyne detection.
Homodyne detection.
Which measures the phase and amplitude of the light wave with extreme continuous precision.
Okay.
You take that continuous measurement data and you feed it into a classical control algorithm, which instantly calculates a feedback signal.
Like real-time adjustments.
Exactly. That feedback signal is then used to modulate the laser drive, adjusting its amplitude or phase on the fly, microsecond by microsecond.
Wow.
By applying this continuous measurement-based feedback, you stabilize the unstable blue detuned regime. This feedback loop prevents the exponential explosion and forces the system into a stable, entangled, steady state.
That's amazing.
This exact mechanism is what allows for the continuous teleportation of quantum states, or even entanglement swapping between two remote mechanical systems.
Okay, let's unpack this. To teleport quantum information, or entangle distant objects, you are balancing a runaway physical explosion using real-time feedback loops based on measuring individual photons. That is staggering.
It's a massive feat of engineering.
But it brings up a massive engineering problem. To do all of this perfectly, your connectors, the things coupling these quantum states together, must be completely, entirely free of noise.
They have to be pristine.
If your nonlinear connector has any static or leaks any information, the quantum state decoheres. It dies. How do we build a perfectly clean nonlinear coupling when we move from optical cavities to our final domain? A superconducting quantum computer.
That takes us to the absolute bleeding edge of the research. Superconducting circuits and a device called the LINC. Let's establish the baseline.
Okay.
In a classical circuit, like the one in your laptop, you get linear behavior from regular capacitors and inductors. But in a quantum circuit, we desperately need nonlinearity to create qubits.
Which are the basic units of quantum information.
Right. We need nonlinearity to create them and to perform quantum gates to actually run calculations. However, you can't just use a normal resistor to get nonlinearity because resistors dissipate energy as heat.
And heat is bad.
Heat instantly destroys quantum information. The foundational solution is the Josephson junction.
The Josephson junction.
It consists of two superconducting metals separated by a nanometer-thin layer of insulator. It acts as a dissipationless, nonlinear inductor. The inductance it provides actually changes based on the amount of superconducting current flowing through it.
Okay.
It gives us the nonlinearity we need to couple quantum states without destroying them with heat.
But the sources point out a huge problem with standard quantum mixers built from these Josephson junctions, like the SNL or the Transwan. They have a really wide bandwidth, which causes major issues.
It does.
My analogy for this is trying to tune an old-school analog radio. You are trying to dial in a very specific radio station to hear a specific song. That song is the desired coherent quantum process you want to activate. But because the mixer's bandwidth is so wide, you accidentally pick up 3 other stations playing loud static at the exact same time. In quantum terms, the sources call these parasitic processes.
Parasitic processes, yes.
The drive power shifts the energy levels around unpredictably, and information leaks out into uncontrolled states. It completely ruins the fidelity of the operation.
That radio analogy is spot on. You want your quantum mixer to turn on a specific interaction at high strength when you drive it, but you want it to be completely invisible and completely harmless when it's just idling.
When it's not being used.
Right. A lot of modern mixers are designed to suppress certain types of mathematical noise when idling, but at high drive powers, higher order nonlinearities, essentially complex mathematical ripples in the energy landscape still bleed through and cause chaos.
Here's where it gets really interesting. The breakthrough device detailed in our sources is called the LINC, the Linear Inductive Coupler. And it is a completely novel quantum mixer design that solves this static problem in a brilliantly elegant way.
The architecture of the LINC is deceptively simple, but incredibly clever. It takes a differentially driven squid, which is just a superconducting loop interrupted by 2 Josephson junctions, and shunts it right down the middle with a standard linear inductor.
Okay, visualize that for me.
Think of a figure 8, where the outer loops have the nonlinear quantum junctions, but the bridge connecting them in the middle is perfectly linear.
Okay.
The genius of the LINC is how it leverages structural symmetry and magnetic flux. When the LINC is idling, when we aren't sending a microwave drive signal to it to perform a calculation, it is biased at a very specific magnetic field, exactly half a flux quantum threading the loop.
Half a flux quantum.
At the specific magic bias point, something beautiful happens. The physical symmetry of the device causes all the nonlinear effects of the junctions to perfectly cancel each other out.
Wait, they just vanish.
The nonlinearity completely disappears. All even and odd nonlinearities vanish. The LINC becomes perfectly linear. It is completely invisible to the sensitive quantum modes it is attached to. It just sits there perfectly quiet, not disturbing the system at all.
It's the ultimate stealth component.
Yeah.
It hides in plain sight until you need it. But what happens when you do need it? When you send that microwave drive pulse to activate a quantum gate.
When you drive the LINC with microwave flux, the outer loop activates. But because the circuit is perfectly symmetric and the drive is delivered differentially, meaning one side goes up while the other goes down, the drive exactly cancels across that center shunting inductor.
Okay.
It doesn't displace the common mode phase of the circuit, meaning the LINC itself stays safely in its lowest energy state. But more importantly, this perfect symmetry enforces a strict selection rule on the physics of the circuit.
And the sources call this parity protection.
Yes, parity protection. The LINC only allows physical processes where the total number of photons in the coupler and the resonators is an even number.
I was trying to picture parity protection, and at first I thought of a bouncer at a club who only lets you in if you show up in pairs.
That's not bad.
But that doesn't really explain how it works physically. It's actually much closer to how noise-canceling headphones work.
That is a much better way to think about it.
In noise-canceling headphones, a microphone picks up the sound wave of the background noise, and the speaker produces a wave that is the exact mathematical opposite.
Right.
When the peak of one wave meets the valley of the other, they cancel each other out, and you hear silence.
Yep.
The physical symmetry of the LINC is doing the exact same thing to those parasitic odd-number processes. The layout of the circuit forces the quantum waves of those unwanted processes to perfectly destructively interfere with themselves.
You've nailed the mechanism. By enforcing that simple mathematical rule of wave cancellation, even parity, It effectively bans a huge fraction of those unwanted parasitic radio stations you mentioned.
They just can't exist.
The physical architecture literally forbids those specific static frequencies from existing. It kills the drive-induced frequency shifts. It prevents the subharmonic parasitic transitions that plague other mixers. It acts as an incredibly clean, protected three-wave mixer. You can use it to perform complex operations like beam splitting or quantum squeezing at incredibly high powers very fast without ruining the delicate quantum information.
And the sources emphasize that this isn't just a fragile theoretical trick that only works on a chalkboard. It's robust in the real world.
It has to be.
Even if the fabrication in the lab isn't perfect, if the two Josephson junctions aren't exactly identical down to the atom, or there's a slight asymmetry in the magnetic flux, the LINC still maintains its parity protection and its quasi-linear idling state to a very high degree.
It's very resilient.
It provides high-Q control in the messy, imperfect reality of a physical laboratory.
Which brings us to the synthesis of everything we've discussed today.
Yeah, let's tie it all together.
Across artificial intelligence folding data spaces, classical bridges absorbing chaotic kinetic energy, microscopic mirrors being frozen by light, and superconducting quantum computers perfectly isolating delicate qubits, nonlinearity is the master key.
It's everywhere.
Linear systems are passive. They just transmit what is given to them according to the rules. But nonlinearity is the exact mechanism that breaks the simple rule of superposition.
Right.
It is what allows a system to become active, to warp geometry, to route energy, and to generate and cleanly control quantum entanglement. Nonlinear coupling is the fundamental geometry of action.
And that is exactly why we study the cheat codes. To the Bus and Sigma scholars of Edward Little High, I want to formally congratulate you for surviving this intellectual gauntlet. You now understand the hidden mechanics of how the universe's most complex systems couple together, break the rules of linearity, and operate at the highest level.
I will leave you with a final provocative thought to mull over.
Oh, let's hear it.
We've seen how the LINC can use perfect symmetry to perfectly hide its nonlinear nature until the exact microsecond it is driven by a microwave pulse.
Right.
If we can engineer that kind of hidden, perfectly linear stealth state at the quantum scale, could we eventually scale that principle up?
What do you mean?
Could we build macro-scale metamaterials, entire skyscrapers, or the chassis of vehicles that appear as totally rigid, perfectly linear objects under normal conditions, but can instantly fold, absorb massive earthquake impacts, and radically change their physical state on command by electronically activating millions of hidden, parity-protected, nonlinear energy sinks?
Now that is a Sigma move. Until next time, keep diving deep.